Welcome to this lecture series on scalars and vectors. We're going to differentiate between scalar quantities and vector quantities, but the focus on this lecture will be basically on vectors. Although we'll consider scalar quantities as we move on. So scalar quantities are those quantities that are characterized only by their magnitude or their size. You cannot describe scalar quantities in terms of direction. Examples are distance, speed. They are all scalar quantities. Distance, speed, mass, scalar quantities. And when you talk about vector quantities are quantities that you can characterize, you can explain, you can describe in terms of their size and their directions. For scalar quantities, they obey the ordinary rules of arithmetic, mathematics. But vector quantities, they don't obey that ordinary rule of arithmetic. If you are adding vectors, for example, you must take note of their directions. Directions must be specified. But when you are adding scalars, you just add, just like normal mathematics, you don't need to think of direction. So we're going to look at how to represent vectors. Assuming I want to represent a vector, I can represent the vector A by writing a bold letter. This is vector A. If I place an arrow on top, the arrow signifies the direction of that vector. So when you see a quantity of this nature, you know it is used to describe a vector. We can also represent a vector, say the vector A, and put something like an inverted V on top, call it a cap. This is also designating this letter as a vector quantity. Again, I can draw a line. Let's say I have a line of this nature. I can also represent this as a vector quantity in the sense that the length of the line gives us the magnitude of this vector, while the direction, the arrow you see at the tip, signifies the direction of this vector. Before we move on, we just talk about some terms involving vectors. When we talk about equality of vectors, two vectors are said to be equal if they have the same magnitude and direction. The same magnitude and direction, we classify them as equal vectors. Then you also have a unit vector. Unit has to do with 1. So a unit vector is one that has magnitude of 1. It has a magnitude or size of 1. Then when you talk about a null vector, for a null vector, the magnitude is 0. Now, let us see how we can resolve vectors into different components. Resolution of vectors into components. So I'm going to wipe this off. Now you may ask, what does this component imply? Let's say resolving vectors into components. When we talk about resolving vectors into components, we are trying to talk about the parts that makes up that vector. Just like you have the human body, okay? You have the legs, the hands, eyes, ears. They are all parts of the human body. They make up the body. So just the way you have different parts making up a single body, the same way you can apply for the vector A. It has different parts that make up this vector. And we can conveniently represent the vector either in 2 dimensions or in 3 dimensions using Cartesian coordinate system. So we can resolve vectors either in 2 dimensions or 3 dimensions, just say 3D, using the Cartesian coordinate system. Now, if I have a vector in 2 dimensions, I want to represent this vector A in 2 dimensions using Cartesian coordinate system. I would say that A, always remember to include a arrow on top to show that that quantity you are describing is a vector. I would say A is equal to A x I plus A y j. In 3 dimensions, I can say, this is for 2 dimensions, please. In 3 dimensions, I can say A is equal to A xi plus A yj plus A zk. Where in our equation I, j, and k are unit vectors. In the x, y, and z axis, respectively. Now, having resolved the vector into components, we can also look at some operations involving this vector. For example, we can add 2 vectors considering their direction. We can subtract 2 vectors also considering their directions, and we can also multiply 2 vectors considering their directions. So assuming I have the vector A, let's assume I have a vector A in 3 dimensions, say AXI plus AYJ plus AZK. Then I have a second vector B is equal to BXI plus BYJ plus BZK. I can add both vectors to give a third vector. I can also subtract both vectors to also give a third vector. So let's see how we can do that. So I'll take this off. In adding the two vectors, we must take note of their directions. Remember, this AX is in the X direction, that's the X axis. AY is occupying the Y axis. AZ is occupying the Z axis. The same goes for the vector B. So when you are adding two vectors that are resolved into their component in this form, you have to add alongside their directions. So for example, I want to add A plus B. I say A plus B will be equal to, I open a bracket, add only those in the X direction. AX is in the X axis, BX is in the X axis. So you add only those two vectors along the X axis. So you have AX plus BX. Close the bracket. I. The I signifies that both of them are in the X axis and I is a unit vector. Plus AY plus BY J plus AZ plus BZ. Okay. If you want to subtract, then you have A minus B will be equal to, you subtract alongside the directions also. So AX minus BX plus AY minus BY J plus AZ minus BZ. Okay. Isn't it that simple? It's very simple. So let's look at a problem involving addition and subtraction of vectors. So assuming I have the vector, I'm going to wipe this out so that it doesn't obstruct our work. Maybe I should just take everything off. So assuming I have the vector A is equal to 2i minus 5j plus 4k I have another vector B equal to minus 2i plus 3j minus k. I have another vector C equal to minus 2i plus 3j minus 4k. I want to add these two vectors, or these three vectors rather. So to add them, I say A plus B plus C will give us a new vector. Let's call that new vector D, which will be equal to, you open a bracket and add alongside the directions 2 plus minus 2 plus minus 2. So you open a bracket, you say 2, or first of all, let's bring out the formula so that we don't get confused. We say AX plus BX plus CX I plus AY plus BY plus CY J plus AZ plus BZ plus CZ K. These are all vectors. So what you have inside the bracket will give you the size. And of course, the I here signifies that is in the X axis, which is X direction. So that unit vector signifies direction. So we have that A plus B plus C will be equal to, what is representing AX here is 2. So we say 2 plus, from BX we have minus 2. So we say plus, open the bracket, minus 2 plus, for CX we have minus 2. So open a bracket again, minus 2. Close the whole bracket, you have I here. Plus, you go to the next column. You have minus 5 here. So we say minus 5 plus, we have minus 5 plus 3 plus another 3, close the bracket, J plus, you have 4 plus, the next one is minus 1 because you have minus K, coefficient of K is 1, so plus minus 1 plus, here you have negative 4. So open a bracket, minus 4, close the entire bracket, you have K here. So that your A plus B plus C will be equal to 2 plus times minus is minus, so you have 2 minus 2, the same thing here, into I plus minus 5 plus 3 will give you minus 2. So minus 2 plus 3 gives you plus 1. So you have 1 into J plus 4 minus 1 minus 4 K. So that this gives you 2 minus 2 is 0. 0 minus 2 is minus 2. So you say minus 2I plus J. 4 minus 1 is 3. 3 minus 4 is minus 1. So we say minus K. So A plus B plus C is now equal to this. So this is the new vector when you combine A, B, and C in the form of addition. Assuming I have two vectors, so I'm going to wipe this off. I consider two other vectors and subtract them. So consider two other vectors. Then we have to subtract those vectors, see how they work. So having two vectors, let's say the vector A is equal to 3i plus 8j plus 4k. We have another vector B is equal to 2i plus 3j plus 2k. We want to subtract b from a, so we say a minus b will be equal to ax minus bx plus ay minus by j plus az minus bz k. So that a minus b will be equal to ax is 3, so we say 3, bx is 2 minus 2i plus ay is 8, put 8 there, by is 3, so we say minus 3, j plus az is 4, bz is 2. We have k. So that your a minus b will give you 3 minus 2 is 1, so you say I. 8 minus 3 is plus 5, so we say plus 5j. 4 minus 2 is 2, so we say plus 2k. So this is now a new vector when you combine a and b in the form of subtraction or their difference. Now we can find the magnitude of this vector separately. We can find the magnitude of this vector b separately. That can actually be done using Pythagoras rule. So if I have a vector, let's say both vectors now, I want to find their magnitude. I use a bar to indicate that I'm looking for the magnitude of a. So the magnitude of a will be the square root of ax squared plus ay squared plus az squared. So magnitude of a will give us, what is ax here is 3. So we say 3 squared plus ay is 8. So we say plus 8 squared plus az is 4. So we say 4 squared. This will give us 9 plus 64 plus 16. So this gives us square root of 89. So that the magnitude of A is equal to 9.43 units. Then for the vector B, we want to find the magnitude of B. So we say just the same way we did for A. So that the vector B magnitude will be equal to Bx is 2, so we say 2 squared. By is 3, we say 3 squared. And Bz is 2, we say 2 squared. So this is equivalent to saying 2 squared is 4, 3 squared is 9, 2 squared again is 4. So when you add this, you have 17, and the square root of 17 gives us 4.12 approximately. So we say the magnitude of B is 4.12 units. So we have come to the end of this video. In the next video, we are going to look at how we can multiply two vectors. Multiplication of vectors either with a scalar or considering multiplying two vectors using the cross product or the dot product. Remember to like my video and subscribe to my channel.